When using parallel cables, it is important to consider the possibility of one conductor failing. This can happen due to damage, loose connections, or other factors. If one conductor fails, the remaining conductors will have to carry the entire load, which can lead to overheating and damage. There are several methods that can be used to protect against conductor failure in parallel cable systems. Firstly, overcurrent protection devices, also known as OCTs, are devices that trip when the current exceeds a predetermined level. They can be used to protect individual cables or entire circuits. In the event of a conductor failure, the OCT will trip and disconnect the circuit, preventing damage to the remaining conductors. Secondly, temperature sensors can be used to monitor the temperature of the cables. If the temperature of a cable exceeds a predetermined level, an alarm will sound and the circuit can be disconnected. This can help to prevent damage to the cables and other equipment. Thirdly, using redundant cables is another way to protect against conductor failure. If one conductor fails, the other conductors will be able to carry the load. This is a more expensive option, but it can provide a higher level of protection. Which method of protection is best for a particular application depends on the specific requirements of the system. In the case of a system with a total current of 850 amps, using two parallel cables of 750 ohm would be sufficient to handle the load. However, it would be advisable to use OCTs to protect the individual cables and to monitor the temperature of the cables. This would help to ensure that the system is protected in the event of a conductor failure. Let us delve a little deeper into each of these protection methods. Overcurrent protection devices are essential for safeguarding parallel cable systems. These devices, such as circuit breakers and fuses, are designed to interrupt the flow of current when it exceeds a predetermined threshold. In a parallel cable configuration, each cable should have its own OCT. This ensures that if one cable fails and the current shifts to the remaining cable, the OCT and the overloaded cable will trip, preventing overheating and potential damage. The selection of the appropriate OCT rating is crucial. It should be based on the ampacity of the cable, which is the maximum current carrying capacity of the conductor. The OCT rating should be equal to or less than the cable's ampacity. Consulting the National Electrical Code, or NEC, is essential for determining the correct ampacity and OCT ratings for specific cable types and installation conditions. Temperature monitoring provides an additional layer of protection for parallel cable systems. By continuously monitoring the temperature of the cables, potential problems can be detected before they lead to a failure. Temperature sensors, such as thermocouples or resistance temperature detectors, or RTDs, can be installed directly on the cables or in close proximity to them. These sensors transmit temperature data to a monitoring system, which can trigger an alarm or automatically disconnect the circuit if the temperature exceeds a safe limit. Setting the appropriate temperature thresholds is critical. These thresholds should be based on the cable's insulation temperature rating and the ambient temperature conditions. The NEC provides guidance on cable temperature ratings and rating factors that should be considered when setting temperature thresholds. Redundancy involves using more cables than are strictly necessary to carry the load. This provides a backup in case one of the cables fails. If one cable fails, the remaining cables can carry the load without exceeding their ampacity. Redundancy can be implemented by using multiple parallel cables or by installing a spare cable that can be switched into service if needed. The degree of redundancy required depends on the criticality of a load and the potential consequences of a cable failure. For critical applications, such as those that support life safety systems or essential industrial processes, a higher level of redundancy may be necessary. In addition to these three primary methods, other protective measures can be implemented to enhance the reliability of parallel cable systems. These include proper cable installation practices, regular inspection and maintenance, and the use of high-quality cables and connectors. Cable installation should be performed by qualified electricians who are familiar with the NEC requirements for parallel cable systems. Proper installation includes ensuring that the cables are properly supported, that they are not subjected to excessive bending or stress, and that the connections are tight and secure. Regular inspection and maintenance can help to identify potential problems before they lead to a failure. Inspection should include checking for signs of damage, such as cuts, abrasions, or corrosion. Connections should be checked for tightness and corrosion. Cables should be cleaned to remove any dirt or debris that could contribute to overheating. Using high-quality cables and connectors is essential for ensuring the long-term reliability of parallel cable systems. Cables should be selected based on their ampacity, insulation temperature rating, and environmental conditions. Connectors should be selected based on their compatibility with the cables and their ability to withstand the expected current and voltage levels. In this specific scenario of a system with a total current of 850 amps using two parallel 750 ohm cables, several factors must be considered to ensure adequate protection. Firstly, the ampacity of 750 ohm copper conductors must be determined based on the appropriate NEC table, such as Table 310.15b16. This table provides ampacities for various conductor sizes and insulation types, considering factors like conductor temperature rating and ambient temperature. It is crucial to select the correct table based on the specific installation conditions. Secondly, after determining the ampacity of a single 750 ohm conductor, it must be verified that two such conductors in parallel can safely carry the 850 amps load. In ideal conditions, each conductor would carry 425 amps. However, varying factors might apply based on the number of conductors in a raceway or cable bundle, as specified in NEC section 310.15c. If derriting is required, the adjusted ampacity of each conductor must still be sufficient to handle its share of the load. Thirdly, overcurrent protection is paramount. Each 750 ohm conductor should be protected by an OCT, such as a circuit breaker or fuses. The OCT rating should not exceed the conductor's ampacity after applying any derriting factors. This ensures that the OCT will trip and interrupt the circuit if one conductor fails and the other attempts to carry the entire 850 amps load. The OCT must have an interrupting rating sufficient to handle the available fault current at the installation location. Fourthly, temperature monitoring can provide an additional layer of protection. While not always required, it can be particularly beneficial in critical applications or environments with high ambient temperatures. Temperature sensors can be installed on or near the conductors to monitor their temperature. If the temperature exceeds a predetermined threshold, an alarm can be triggered or the circuit can be automatically shut down. Fifthly, proper installation practices are crucial for the safe and reliable operation of parallel conductor systems. The conductors must be properly supported and secured, and the connections must be made with appropriately sized and listed connectors. Torque specifications for the connectors must be followed to ensure a secure and reliable connection. All work must be performed by qualified electricians familiar with the NEC requirements for parallel conductor installations. Sixthly, regular inspection and maintenance are essential for ensuring the continued reliability of the parallel conductor system. Connections should be periodically inspected for tightness and corrosion. Conductors should be examined for signs of damage or deterioration. Any issue should be promptly addressed to prevent potential failures. Seventhly, documentation is key. Detailed records of the conductor sizes, ampacities, OCT ratings, and installation details should be maintained. This documentation will be helpful for future maintenance, troubleshooting, and upgrades. It is also important to keep records of any inspections or maintenance performed. Eighthly, consider future load growth. If there is a possibility that the load will increase in the future, it is wise to design a system with some extra capacity. This can be achieved by using larger conductors or by adding additional parallel conductors. Ninthly, coordination studies are important for large electrical systems with multiple OCTs. A coordination study helps to ensure that the OCTs will trip in a coordinated manner, minimizing the extent of any outages. This can be particularly important in systems with parallel conductors. Tenthly, consider the type of load being served. The type of load can affect the selection of OCTs and the need for additional protection measures. For example, motor loads can create high inrush currents that can trip OCTs. In such cases, special OCTs designed for motor loads may be required. Let us now discuss the NEC requirements for parallel conductors in more detail. NEC Section 310.10H outlines the requirements for paralleling conductors. This section states that conductors size 1/0 American wire gauge and larger can be run in parallel provided that all of the following conditions are met. 1. The conductors are the same length. 2. The conductors are of the same conductor material. 3. The conductors are the same size and circular mill area. 4. The conductors have the same insulation type. 5. The conductors are terminated in the same manner. 6. The conductors have the same ampacity rating. 7. If run in separate raceways or cables, the raceways or cables have the same physical characteristics. 8. The equipment grounding conductors are installed in parallel in accordance with Section 250.122. These requirements are intended to ensure that the parallel conductors share the load equally and that the system is properly protected. If these requirements are not met, the parallel conductors may not share the load equally, which can lead to overheating and potential failures. In addition to the requirements in Section 310.10H, other NEC sections may apply to parallel conductor installations depending on the specific application. For example, Section 250.122 outlines the requirements for equipment grounding conductors, and Section 300.3b outlines the requirements for the installation of conductors in parallel raceways. It is important to consult all applicable NEC sections to ensure that the parallel conductor installation is compliant with the code. It is also important to consider the environmental conditions in which the parallel conductors will be installed. For example, if the conductors will be exposed to high temperatures or corrosive substances, they must be properly protected. This may involve using conductors with a higher temperature rating or installing the conductors in a corrosion-resistant raceway. In summary, protecting parallel cable systems from conductor failure requires a multifaceted approach that includes overcurrent protection, temperature monitoring, redundancy, proper installation practices, regular inspection and maintenance, and compliance with the NEC. By implementing these measures, the reliability and safety of parallel cable systems can be significantly enhanced. The specific protection methods and requirements will vary depending on the specific application and the environmental conditions. It is important to consult with qualified electrical engineers and electricians to ensure that the parallel cable system is properly designed and installed. In the specific case presented, with 850 amps of total current and the intention to use two parallel 750 ohm cables, it is crucial to verify that the ampacity of the 750 ohm cables, after any applicable dating, is sufficient to handle the load. Overcurrent protection devices, such as circuit breakers or fuses, should be installed for each cable, with a rating not exceeding the cable's ampacity. Temperature monitoring can provide an additional layer of protection, especially in critical applications. Proper installation practices, regular inspection and maintenance, and compliance with the NEC are essential for ensuring the long-term reliability and safety of the system. Therefore, a comprehensive approach that considers all of these factors is necessary to effectively protect parallel cable systems from conductor failure. Remember to always consult the latest edition of the National Electrical Code and to seek guidance from qualified professionals when working with electrical systems. The information provided here is for general educational purposes only and should not be considered a substitute for professional advice. Working with electricity can be dangerous, and it is important to take all necessary precautions to protect yourself and others from harm. Always to energize circuits before working on them and use appropriate personal protective equipment such as gloves and safety glasses. If you are not comfortable working with electricity, it is best to hire a qualified electrician to do the work for you. By following these safety precautions, you can help to ensure that you and others stay safe when working with electricity. Remember that electrical codes and regulations can vary depending on your location, so it is important to consult with your local authorities to ensure that you are complying with all applicable requirements. Staying informed and following safety guidelines are essential for preventing electrical accidents and ensuring the safe and reliable operation of electrical systems. Always prioritize safety when working with electricity, and never hesitate to ask for help if you are unsure about something.